Hi, we are international college students. Here we present our embedded system software project, Buckley, the self-balancing robot using Raspberry Pi. Let's begin with the system overview. Smart products requires a system that can autonomously and repeatedly do the task. In this project, we build a smart self-balancing model which can balance itself with similar to smart products like hoverboard, scooter, and so on. The system composed of a Raspberry Pi as main processor that reads sensor value, process, and send out PWM to the motor driver to rotate the wheel. The reason we use gyroscope with accelerometer is because, first, the gyroscope has a drift. All the lead value at the same point is not equal when the time passes by. The usage of gyroscope is to measure the rate of change of the angle, while accelerometer measures acceleration and the output is not stable. But the accelerometer does not have a drift, so we take advantage of both sensors. I will use accelerometer to measure the angle value. The concept of the system is to balance itself by going toward the tilted direction to keep the balanced state, when the model is tilted as shown in the picture. For software development, we use three main skills and techniques: sensor reading, PD control, and complementary filter. PD or proportional derivative controller is a control loop feedback mechanism commonly used in industrial control systems, where P stands for proportional current error and D stands for derivative rate at which the error had been changing from the weighted sum of all three. The flow of the system starts from reading the value from sensor, then calculate the angle from the angle values. After that, the error can be calculated by subtracting the balance set point from the angle. If there is an error, it means the model is not balanced. We have to compute PID control value and move the wheel. Another process we take into account before running the code is PD tuning. PD tuning is the process of finding the values of proportional and derivative gains of a PD controller to achieve desired performance and meet design requirements. We start by setting our gains to 0, Kp and Kd, where gain is defined as the change in input divided by the change in output. The more gain a controller has, the faster the loop response and more oscillatory the process. Second, increase P until the response is steady oscillation. Third, increase D until the oscillation go away. And 4. Repeat the step 2 and 3 until increasing the D does not stop oscillation. Finally, set P and D to the last stable value.
And now I will talking about the problems we encounter during the project. The first problem is PID tuning. While we doing this project, we increase or decrease the gain dramatically, and that occurred the overshoot. Then the robot will transition between the low error state and high error state. The solution is to increase or decrease gradually. The second problem is the motor type we used. We used the normal DC motor which do not come with the encoder. because encoder model can feedback the speed and position of the model, which is very important in PID tuning. The third problem is that this project required control engineer knowledge, so all document and block related to this project is written in control engineer term, so it's much more harder for us to do this project. And now we will show you the demonstration of our project. You can clearly see that the robot can balance itself for a while and then it will fall. These are all the reference we use in the project. I will also put it in the description.